In this lesson on exponential and logistic functions, our goals are to recognize exponential growth and decay functions, write an exponential function given the y-intercept and another point from a table or a graph, be able to define the number e, use transformations to graph exponential functions without a calculator, recognize logistic growth function and when it is appropriate to use a logistic growth model to answer questions in context. So far, we have discussed the polynomial functions, linear, quadratic, cubic, etc., and rational functions. In all of these, the variable x was the base. In exponential functions, the variable x is the exponent. Exponential equations will be written as the following. F of x equals a times b raised to the x, where a is our initial value, and a cannot equal 0. Exponential functions are classified as growth if b is greater than 1, or decay if 0 is less than b is less than 1. Let's try the first example. Determine a formula for the exponential function whose graph is below. Notice the function is getting larger as x gets larger. This is exponential growth, so we know our b value must be greater than 1. Let's start with our function. F of x equals a times b to the x in its general form. We know our y-intercept is 2, shown in the graph. So we know the point is 0, 2, and we can substitute it into our equation. So we have 2 equals a times b raised to 0, and we see that a equals 2. We can also just replace our a with 2 because the y-intercept here represents the initial value of the function, which is where our function is evaluated at 0. So we know we can use this, that our y-intercept equals the initial value of the function. We also know that the point 2, 6 is on the function, as shown in the graph. We can substitute in 2, 6 into our equation and solve for b. So we'll have 6 equals 2 times b raised to the 2. We can divide by 2 and we'll have 3 equals b squared. We can take the square root of the square root of 3 equals b. And note, since b must be positive as defined in the exponential function, we can only use our positive square root of 3. Now we'll rewrite this as 3 to the 1/2 equals b. So now we can build our equation. We have f of x equals a, which is 2, times b, which is 3 to the 1/2, raised to the x. Simplifying, we'll have f of x equals 2 times 3 to the 1/2 x. And this is our function, our equation for this function in the graph below. Now, let's move on to the next example. We're going to describe how to transform the graph of f of x equals 3 to the x into the graph of g of x equals 3 raised to the x plus 2 minus 1. Let's use our transformations we learned in Unit 1. Since the plus 2 is inside the function, we know that we will move left 2. And since the minus 1 is outside of the function, we will move down 1. And that is it. Now let's try sketching a graph of an exponential function using these transformations. Here we have g of x equals 3 raised to the negative x. This means we will reflect over the y-axis. We also have the point 0, 1 since if we put in 0 here, we'll have g of x equals 1. So here's our point 0, 1. We have a horizontal asymptote at y equals 0, which is characteristic of exponential functions. And we know this is decay. We know this equation is decay because it can be rewritten as g of x equals 3 to the negative 1 raised to the x, which means g of x equals 1/3 raised to the x. Here we can see our a value is 1 and our b value is 1/3, which is between 0 and 1. Therefore it is decay. So we can sketch our graph like so. Now, let's look at g of x equals -3 raised to the x plus 2. We know we'll reflect over the x-axis since the negative is outside the function. And we know we'll move up 2 because of the plus 2 outside of the function. So we'll have our horizontal asymptote is originally on the x-axis. So we reflect over the x-axis, it doesn't move. We move it up 2. And we start with the point 0, 1. We reflect it over the x-axis to get -1, 0, -1. And then we'll move it up 2. We end up back at the same place. So here's our point, and we know our function will look like this. Now let's look at the number e. Many exponential functions in the real world, ones that grow and decay on a continuous basis, are modeled using the base of e. Just like pi is approximately 3.14, we say e is approximately 2.718. We can also define e using the function quantity 1 plus 1 over x raised to the x as follows. As x approaches infinity, 1 plus 1 over x raised to the x approaches e. Let's try convincing ourselves that this function approaches e using the table function of our calculator. So we can graph 1 plus 1 over x raised to the x, and then we can look at the table, and we'll see it's slowly increasing, and then starts increasing a little bit faster. And now let's look at a very large number of x, say 10,000. This will get us x approaching a much larger number. We can look at our table, and we can see that our y value is 2.718. So here we can see our function is approaching this value. Now this is rounded because of the table. Now let's look at applications of exponential functions. Do you think it's reasonable for a population to grow exponentially indefinitely? Here's where logistic growth functions come into play. Logistic growth functions are functions that model situations where exponential growth is limited. The equation will be of the form f of x equals c over 1 plus a times b to the x, or it'll be written as f of x equals c all over 1 plus a times e to the negative kx, where c is our limit of growth. The graph of a logistic function looks like an exponential function at first, but then it levels off at our y equals c. Remember from the parent functions in Chapter 1, the logistic function has two horizontal asymptotes, y equals 0 and y equals c. Now let's look at an example. The number of students infected with the flu after T days at Springfield High School is modeled by the following function. What is the initial number of infected students at T equals 0? To find this number, we just substitute 0 in for T. So we'll have P of 0 equals 1600 all over 1 plus 99 e to the negative 0.4 times 0. This leaves us with 1600 over 100, which equals 16. So initially, there are 16 students infected with the flu. Now let's look at 5 days after that. T is in days, so if we want to find out how many students are infected after 5 days, we'll just substitute in 5 for T. P of 5 equals 1600 over 1 plus 99 e raised to the negative 0.4 times 5. And if we evaluate this, we'll be left with approximately 111.125. So about 111 students will be infected after 5 days. Say we want to know the maximum number of students that will be infected. This is where our limit of growth becomes useful. Here, in this equation, our limit of growth of 1600. This means the maximum number of students that can be affected is 1600. Now, according to this model, when will the number of students infected be 800? So we want to find out when 800 students have the flu. So we set our equation equal to 800. And to find what T equals, or to solve for T, we're going to have to graph this. So we'll graph one line, y1 is 800, and our y2 will be 1600 divided by 1 plus 99 times e raised to the negative 0.4 x. And we can graph this. And then we're going to calculate the intersection between the two lines to find our value for T. So I can calculate 5. Here we can see that after 11.487 days, we can round this to 11.488. So about after 11 to 12 days, there will be 800 students infected. For our last example, let's try and graph a few logistic functions. We know our y-intercept is at x equals 0, so we can substitute 0 in for x and solve. So we'll have f of 0 equals 9 over 1 plus 2 times 0.6 raised to the 0, which equals 9 over 3, which equals 3. So our y-intercept is the point 0, 3. Now we know we have a horizontal asymptote at y equals 0, and because our c value here is 9, we know we also have a y-intercept, or horizontal asymptote at y equals 9, which is up here. Now our logistic function will start similar to an exponential function and then begin to level off as it approaches that second horizontal asymptote. Similarly, for the next problem, we can substitute in 0, so f of 0 equals 8 over 1 plus 4 e to the negative 0, which equals 8 over 5. So here our y-intercept is the point 0, 8/5, which is approximately there. It's 1.6. Now we know we have a horizontal asymptote. y equals 0. And we know we also have another horizontal asymptote at y equals 8. Up here. And it again will start like an exponential function and then level off as it approaches that second horizontal asymptote. And that is it for this lesson.